Hello, I'm John Levy, the CEO of Seek. Today we're going to walk around and we're going to see how we design chips, how we manufacture them, how we test them, how we integrate them, and in fact how we integrate them into a full quantum computer that we're seeing right here.
As you can see, the chip design itself essentially comes down to a CAD drawing or like what looks like a piece of artwork where it's just shapes, and these shapes all represent metals or other films that end up being deposited onto a substrate. So this is a centimeter by a centimeter. And so in this tool I can design or I can draw different shapes and the different layers that they physically appear on the chip. So most of our chips consist of several chips. So a bottom chip and a top chip. Here they are superimposed on each other. Here are all of the metallizations that are on the bottom chip, the carrier chip. And then there's a second chip that contains the qubits. So here, this is the quantum chip, and it's this much smaller chip here. And all this contains is qubits and their associated readout resonators, which are these little windy lines here. And then this chip gets bonded on top of the carrier chip to make the total device. So the carrier chip, this gets fabbed in-house in our own fab, and then the flip chips we order from a quantum foundry. And then we receive these chips and bond them together to make these MCMs. And this is what we're currently measuring. So because it's modular, it means that we can verify the functionality of the most complicated stuff before we actually take the time to assemble and potentially sacrifice a flip chip. So we can take just this bottom chip, test it at 4K, and verify that it's functioning, and then we can go and make a bond and actually make an MCM, and then we can proceed further with the testing. I do physics simulations and circuit simulations to find the target circuit parameters, but then you have to make a physical shape that gives you the correct circuit parameter. And to do that takes a lot of creativity, because there's kind of infinite solutions to that problem. So you can make any number of shapes that give you the right electrical characteristic. And so it's kind of like your own thumbprint on the design, because you made it look a certain way, even though there was probably 1,000 solutions that would have done the same thing.
So here we have our measurements lab. This is where we can figure out the thicknesses of some of our chips for some of the layers of metal or insulators. So we have different equipment with lasers and sensing technology. We could figure out stress on our wafers, uniformity, things like that. Hi, I'm Asa Chamble-Jacobs, and I'm a facilities and equipment engineer. That means I try to keep all of this stuff running. This here is a sputtering machine, which we use to deposit our niobium, our aluminum manganese, and our molybdenum. So a lot of our wires are actually made of niobium because it superconducts at low temperature. So in here, you can load wafers onto a pallet that looks like this. And we could put glass slides to use for measurements on the other tools that we have. After it goes in there, we could do a little bit of an argon sputter etch to clean off the wafer of any oxides. Then we can choose to deposit which one of the metals that we want for a certain amount of time, and that will determine the thickness of the niobium deposited. This is our NAG sputterer, MRC. And this one just has two different metals. Right now it has copper and titanium, which we're using for some of our resistor experiments. This is an old evaporator that we have that we can deposit layers of titanium and mostly indium in this system. It works by using electrons to melt metals in a crucible like this to the point where they are evaporated and it kind of floats up onto the wafer that's above them. So you get a very thin layer that's more evenly dispersed. You have these little metal pellets that go into the crucible, and they're melted when they're hit with a beam of high energy electrons. This is a PCVD tool we use to deposit silicon nitride. That is used as an insulator to protect your resistors and your wires from interfering with each other. It also has an added benefit of being clear, so you can see through it to see all of your features underneath. We have lines here for our gases that come in. We have silane, ammonia, argon, nitrogen, hydrogen that go into the tool, and these are the exhausts that go out, which are then sent to a scrubber, cleans them before they're released to the atmosphere. This is the CHA evaporator. We use this tool for our titanium, gold, palladium depositions. It has a carousel on top, so it can do up to 9 wafers at once. You can see here we have some dummy wafers that'll have different layers of metals on them, which we can then use to get the right resistances that we're looking for. Coolest machine, I think this one, because it's evaporating things like gold, metal, titanium, stuff you don't normally get to play with in your everyday life.
This is a Kurt J. Lesker Luminos DC sputtering tool. We use this 4-inch targets, interchangeable. We right now use it with the DC sputter molybdenum. I'm John Vivaldo. I'm a senior process engineer here. Been here for quite a long time. This will open up, an arm will come out. We'll load a 150 millimeter wafer on the arm. The arm will bring it back in, rotate, deliver the wafer into the chamber, and then we run whatever the recipe happens to be, or whatever you want. This is another tool made by Kurt J. Lesker. It's a DC sputtering tool similar to the other tool. And this tool we use exclusively to make the Josephson junction. It's one of the primary features in the superconductor industry. So that's all done exclusively in this tool. This is actually the coolest machine for me. It's a completely manual tool. I enjoy running it. It has a lot of valves and everything you need to manipulate to get the desired results that you like. Sometimes it's a lot funner than just kind of pressing a start, hang out. Here you have to manipulate everything in the correct order to get the desired results. So I enjoy this machine, I enjoy working on it. This is the latest addition to the fab. It's a deep silicon etcher. Basically, it's used to, we use it to etch vias through the silicon so we can access the back side of the wafer. We're hoping at some point in time to have metrology and circuits on both sides of the wafer. These are all the chases where we keep all our gases, all the tools, whether it be the ride tools, the sputtering tools, the evaporators, they all need different gases. So this is a gas farm. We have argons, oxygen, nitrogen, helium, nitrous oxide, SF6, HF3. Whatever gases we need are here. This is a plasma lab. 3 of the tools here are used for etching. One of the tools is used for deposition. These tools are reactive ion etchers used for etching. This is a metals tool. We etch molybdenum, niobium, titanium, tantalum. That's all done in this tool. We use sulfur hexafluoride, SF6 or CF4 to etch all the metals here. This tool is an inductively coupled plasma etcher. We use chlorine or trichloride. We use it to etch niobium, aluminum. That's all done in this tool. The last tool in this lab is the Plasma Enhanced Chemical Vapor Deposition tool, again by Samco. It's a single wafer. The chamber opens up, you load the wafer in, and it uses TIOS, tetraethioxysilene, and oxygen to deposit an oxide on your wafer surface. It's very conformal.
Hey Mario,
Hi.
what do we got here?
So here is a chemical mechanical polishing machine, and what it does is it smoothens and flattens a layer of our wafers so that we could add more complexity to our chips. A wafer is held by vacuum by that polishing head there, and a slurry, which is a chemical mixture dispersed with nanoparticles, is put onto that pad there, and the polishing head applies mechanical force combined with that slurry to smoothen out and flatten that surface. The most fun part is to see the results in that dilution refrigerator after everything's said and done. My name is Mario Rinzullo, and I am the Senior Process Engineer here at SEEK.
How are you?
Yeah, this is a box. I'm going to start putting wafers in there. I'm going to start processing wafers. This is the first step where you need this kind of boxes back and forth from different labs. I'm Daniel Johannes. I am the fab lead here at SEEK. So this is our lithography room where we do all the lithography steps. So myself and Mark will work on this area.
Hey Mark.
Yeah. So all the systems here we see they use UV light to basically expose this pattern that we have, this different pattern that you see in here, and translate these patterns into the resist. This machine is the one that we first put the resist on in one of these chambers here, and then some baking chambers here. So once it puts the resist in there, so this one is 1-to-1. Basically, whatever you see here will be directly printed onto a wafer. And then we have this one, which is 5 times reduced in size and exposed into wafer. So using that machine that you see over there. Mark is working on the stepper. This is a 5x reduction stepper where you saw this mask over there. So it basically sends UV light, like a deep UV light through the mask. Wherever it's not exposed, goes through the mask and exposes the wafer. Yeah, that's a 6-inch wafer, 150 millimeter wafer. Yeah, so that's a size. You can see, as you can see here, like those are the different panels. Basically, in this one, we have 3 different masks that are being printed.
First, we design our chips, and then we manufacture them in-house in our fabrication facility across the street. Then those chips, after being manufactured, are being diced, and then being brought here. And here, this lab, we have 3 different temperatures, 3 different platforms at which we can test. 4 Kelvin, we just dunk it in liquid helium in next door lab. This is 100 millikelvin, and we have also dilution refrigerators of 10 millikelvin or so in the next lab. Those are dilution refrigerators. Both of them are cold right now, and temperature of the sample stage right now of this one is slightly more than 8 millikelvin. Slightly more than 8 millikelvin. Yes. We have current sources here also. We have digitizers, we have amplifiers, we have mixers. Everything here in this like PXI. And it's also being remotely controlled. One of those modules, it's nothing more, nothing less, just that's a computer, portable computer, which controls everything inside here. And this is wires are being run to this dilution refrigerator down to millikelvin temperatures. Here we're testing our 5-qubit quantum computer, which is being tested right now, again, remotely by people. And all these tests are being run from England. So again, like I mentioned a few minutes ago, chips were fabricated across the street, and then they're brought here already diced. And usually we have chips in different form factor, either 5 by 5 millimeter chips, which are smaller, or 10 by 10 millimeter chips, which are bigger chips. And for these different chips, we have different packages, different probes, immersion probes, and different packages for millikelvin. For me, at least, I mean, a lot of things here, it's pretty cool. For example, this dilution refrigerator. When I started my career, it was like quite a long time ago. These machines were pretty difficult to operate, and it was just fuse those machines in the wall. Now those machines are pretty standard, so they just call refrigerators in them. So basically people buy them. Delivery time is kind of not one day, not few days, maybe a few months. But after they delivered, you could plug them in, or press the button, and let's say 24 hours, 30 hours or later, you have like millikelvin temperature, close to absolute zero, which is still kind of, I'm Igor Vernik. I'm Director of Testing and Development, and I lead all measurements here at SICK at ALSA.
How you doing? I'm doing our 4 Kelvin testing in liquid helium right now. So I'm controlling our equipment and our hardware, which you see behind me here, and those are connected to our shield room. And inside of the shield room here, we have one of our 4 Kelvin wet probes, and it is dunked into our dewar of liquid helium here. Upside down, it's all the way, the chip is all the way in the bottom, and these are our room temp connections up here on the top. My name is Jason Walter. I'm a senior engineer, testing and design. Been here for about 7 years now. There we go. So this is our 4-output switch control demultiplexer, in which I am addressing each of these 4 outputs by turning my 2 switches in a state of either 00, 10, 01, or 11 to address each of the outputs in series here. So when I address each output in turn, I expect to have my input clock pass through to the appropriate output, which is what I see here with each output in turn triggering, and none of the other outputs triggering when they're not supposed to. This is a good working circuit, which we are then planning to use this physical carrier chip to bond with one of our quantum chips to make a multi-chip module. So I'm pre-screening at 4 Kelvin right now to make sure that our SFQ circuitry, control circuitry works correctly for further testing at millikelvin and to have it talk to our quantum chips. This is our large bottom chip that has all of our SFQ control circuitry, and then we take a smaller flip chip that has our qubits and quantum circuits on it, and we physically put them together, squeeze them together with specific lines so they can communicate and be magnetically coupled. And then by only accessing our control circuitry, we can communicate and modulate and set our the qubits, the quantum circuitry, without physically directly talking or communicating with the qubits themselves, only the control circuitry. That's our final goal, right? Is to have everything be controlled by our SFQ control circuitry, and not have to control each of the qubits individually.
Thank you.